Good morning. It's February 17th, Monday, 12:40 p.m. Good evening. CS 797K, Lecture 8, Triple Parity and Beyond. So this is supposed to be a short lecture. So we'll just do this lecture quickly and discuss some of the questions for midterm. So basically, we'll just try to solve. We'll just try to take one of the primitive polynomial and try to build a logarithmic table in this class. So your midterm is in this month. I guess you all are aware of that, right? Okay. We have two midterms and one end term, and one of the midterm is in this month, by the end of this month. Assignment? Announcement? I'll make an announcement. I need to check the dates, but I'm sure that your midterm is this month. Okay. First midterm. And I guess you are also having a tour with NetApp. I don't know where's the process going on, but if we are lucky, we'll have a class with a tour to NetApp. Okay. And also for the projects, the South Dakota has given us the linear box, Linux boxes. So we are good to start with our projects. So I'll make an announcement with a spreadsheet. Just try to form a team. I guess 3 or 4. I'll just make an announcement saying how many members you can form. Just try to collab and form a team. Just try to make a team name and enter it beside your name on the spreadsheet. I'll try to make an announcement and we'll start our project after the midterm. But try to make your project groups now. Okay. So this lecture is on triple parity and beyond. Till now we have discussed about two parities, RAID DP or RAID RDP. So a diagonal parity and a parity. The parity can be counted using exhaust, and the diagonal parity is counted using some of the mathematical equations we have shown in the past lectures. So we have discussed about two parities. We can go beyond two parities, and we are going to discuss triple parity in this lecture. It's relatively simple, but computationally expensive. Course outline. We're just here at the block-based protection. We just finished our Hamming code, and we have saw what are raids and raid 1 to 10. 1, 2, 3, 4, 5, 10, RAID DP, RAID RDP, and Solomon, ISBN, and stuff like that. And today we're going to see the triple parity. So we are yet to discuss compression, file-based system, data management, moving, and other topics on cloud virtualization and stuff. So for the midterm, you're going just to have Hamming code, ISBN, building logarithmic tables, and about the RAID. Those are some simple stuff. You no need to memorize any formulas. Okay. Triple parity, RAID 7.3. You can see in this paper. Let me open that and look what's inside. So it's about triple parity. So this was published in 2009. No. Good PDF. Yeah. Guess this should be. Yeah. You can go through the paper if you want. It's right here. You can just go ahead and read the paper. It's not necessary for this course, but you are really interested in RAIDs. You can go through that and learn the mathematical concepts beyond that. And they'll just try to explain the previous stuff in their methodologies and everything. So you will get to know what are previous products on that, what's the cons of the previous products, and why are they building triple parity now, and everything in detail. So implemented by Sun Microsystems in ZFS in 2005. So that's the source code right there. You can go into the source code if you like. And it's actually complex to understand, but whenever you have code, you can go through the code and understand what's the process going on inside a RAID. So what are the computations going on inside a RAID? It's very difficult to explain stuff in mathematical equations. But if we have code, we can just go through the code and understand what's going on. So this is the code here, and the repositories. Oh, multiple repositories, ZFS. Just look for source config. Yeah, if you are aware of all the file systems, you can just go through there and get code, which I'm not going to do now. Just showing you we have code that was implemented in Sun micro systems. So other companies also used triple parity, such as Radix, but it's not worth of going there and checking it out, because it's not the best product out there in the market. That's just the marketing strategy. There's nothing they have built with the triple parity, but that's just the marketing stuff. So it's junk. If you are interested, just go there and check out these products on RAID triple parity. So this Sun Microsystems used it in ZFS files in 2005. Next, PQR read Solomon coding. So N data drives, and we have 3 parity drives. For example, if we have like 12 data drives, we have 3 more parity drives, which gives us 15 drives in total. So we have N data drives and 3 parity drives. We can arrange the parity drives like any like in any order. For example, if you see the last time RAID RDP, diagonal parity, we have a dedicated parity drive, and we also have a diagonal parity. So that's not dedicated drive, but we have the data, parity drives just scattered in every stripe, not just dedicated to a single data drive. So you can make any changes to the design as you like. So they have these log sheets where you can go and find how they designed their product. So for example, if you want to see what's the parity drive inside a particular RAID, you can just go through the documentation and see which bit is dedicated to the parity. So it's not like dedicating an entire block to a parity. You can also make changes as you like. You can just make scattered, and the company may make a sheet like this is the parity bit, this is the parity bit. So you can just go there in the documentation, see what are the parity bits inside a RAID. So it's not like always giving one particular the entire data drive with the parity. So they have n data drives and 3 parity drives. So we have n plus 3 drives in total for a RAID for 3 parity 3. So the first parity, so we'll say it like PQR parities, P parity bit, Q parity bit, and R parity bit. So these are the simple equations. But if we increase the number of drives, the math get complicated. It's easy for the formulas, it's easy to see in the formula, but when it comes to real world, increasing the number of data drives, the complexity increases. So we just can't do the math on paper. It's we can always write coding. So p parity, it's a simple XOR as we discussed till now for all the RAIDs. It's simple XOR. So just 2 power 0 is always 1. So 1 is multiplying with the data bits and getting XORs. So we'll XOR an entire stripe and get a parity bit. So that's p parity. Coming to Q parity. So each drive double the previous. So we're just giving powers here, 2 power 0, 2 power 1, 2 power 2, and so on till 2 power n minus 1 for the n minus 1 drives. So simple, we'll just do these simple XOR calculations, but we'll multiply it with the doubling the previous one. For example, here for drive 0, we have just considered 1. 2 power 0 is, we'll double it in the next drive, in the next iteration with it, if you're doing a code. So it's 2 power 1, 2 power 2, and so on until we have n minus 1 drives. It's power n minus 1. So that's Q parity. Why is it n minus 1 drives here? Why isn't it n? Yeah, so we are including the two other parity bits as well, P and R. So this is the Q drive. So we're calculating one. So if it's N, we're calculating one drive. So it's N minus one drives. We're just XORing N minus one drives. It's Q parity. It's R parity. So now we're instead of doubling it, we're multiplying it with 4. We have 4x. Okay. So 2 power 0, 2 square, 2 power 4, and so on and so forth till n minus 1. So this is how we calculate the R parity. It's simple calculation for because we are just thinking about n equal to 5 or 6, but it gets complicated with increasing in the number of n's. Okay, so that's how we calculate PQR for triple parity drives. So this is the basic concept which we are planning to discuss in this lecture. That's why I said it's simple and short lecture. So no theoretical limits. So we can just build any number of n drives and we can just make the calculation. So there is no theoretically limit to the number of parities, to layers of parities, but practical limits exist. For example, we run out of letters, or also the math gets complicated with each layer as we discussed earlier. 5. So NetApp RAID triple parity, RTP in NetApp. So already covered in the previous lectures. So NetApp has used many products. So N data drives, one RAID 4. So let's see what this one is. So yeah, so one RAID 4 parity drive. So row R, one diagonal parity, one anti-diagonal parity. So RAID triple parity, it's using one diagonal parity and one anti-diagonal parity. As I said, it's not always dedicating the entire parity to a single data drive. We can just scatter that thing. The thing is, we need to note it. We need to make a documentation what's every bit is about. So if they do that, then they can scatter anywhere they like. So the NetApp product used diagonal and anti-diagonal parity stripes for the parities. So parity rotated regularly among drives to avoid hotspot. So they used to rotate regularly in the drives to avoid hotspots, to make everything concentrated one thing. They used to just diverse the parity drives. So uses fake missing diagonal stripes. So as we discussed earlier in raids, there is sometimes missing diagonal stripes. Yeah, so if we want to make one more diagonal stripe, we need to extend one more stripe and we need to add it. So we have some missing diagonal stripes. So they used fake data to cover up the missing diagonal stripes. So they just given some fake data to do that. So value that would be on diagonal parity drives can be calculated with XOR. So everything in parity is an XOR. I think you will be noticing by now. So this is the netapp.com publications on RAID triple parity. So this is something interesting. So RAID triple parity, you can just go through this paper and you can see the PDF. So this is the RAID 3 when the NetApp used it for the product. They just published it in the NetApp. So there are a lot of calculations here, of equations. So if you are really interested to know the math inside a RAID, you can just go through all of this stuff. So I didn't have time to go all of this stuff, but hopefully I'll go through this stuff this semester. I'm teaching, but I haven't went through the stuff yet. And what's this? Yeah, this is the same thing. We just it directly uses the paper. We can just download the paper from that link. Next, fake data. So we just discussed the fake data. So the missing diagonal stripe will be given fake data. So is it really fake? No, it's not. So there is some computations going on in the background to give the fake data as well. So the data was not really useful, but it's not really fake. Okay? So it's not really fake. Placeholders for data assumed to be 0. So at first they'll initialize the stripe with 0, the missing values with 0, RAID RTP uses a zero-field fake horizontal stripe after each diagonal extent to simplify calculations during rebuilding. So if they are using some fake diagonal stripes, so like giving some random numbers, it's hard for them to recognize the fake drives and then recalculating if one of the drive was corrupted. So to avoid this, they are using the zero field fake horizontal stripes. So RAID DP also needs fake data. As diagonal parity also needs fake data. RDP we discussed earlier. If the RAID 4 R4 does not contain a prime number of drives, the diagonal stripes will be disjoint. Yes, we discussed about this prime numbers previously. The number of drives should be in prime for RAID RDP to avoid um, any missing stripes, diagonal stripes in that RAID. Keyword example. Okay. Thin provisioned volumes. Most disk volumes are only partially full. By virtualizing storage, presenting a pseudo disk with variable capacity, we can more efficiently use the physical storage. Yes. So cloud storage. So one of the example for that is cloud storage. So if using less data to store, so we are using like only half of the memory size of RAID to store the data. That's the example with cloud storage. We'll just pay on as we use that. So we'll pay for that. We use, so whatever we use, we pay for that. So that's a cloud storage. To the users, it looks like an infinitely expandable volumes, right? So we can just store any amounts of data in the cloud. It's not like storing infinite number of data, but the thing is uh, the store owners, I mean the cloud storage owners, they're trying to build more of the drives that are capable of storing all the information present in the world. Okay, so that's what is going on. So for the users, it will be like infinite expandable values, but it's really not. They need to have something to store the data. So that's where again this RAID comes. So that's what we are discussing the RAIDs. So it's a cloud. So it's a cloud era, but the cloud also need to store the data somewhere, right? So to the vendor, it might be just another file of their network, replicating to different data centers like RAID 1. It might be virtualized to multiple data servers like RAID 0. So that's basically this slide is all about. Metadata, the key to thin provisioning. Yeah, as I said, they will document the things like for every data bit, there is some documentation going on. So that's called metadata, the key to thin provisioning. So standard RAID levels allocate data algorithmically. So as per the code they give, that's why there is a lot of source codes in the links we shown. So according to those source code, it will directly allocate the things. So by learning by understanding the code, that's equal to the understanding of metadata. So volumes block 0 to 1023 on drive 0, 0 to 1023 volumes 1024. So parity for the above blocks of drive and block 0 to 1023. So this is just explaining one RAID 4. So each of these is one block of code. I mean one block in the RAID. It's just an example explaining how the things working inside RAID 4, and this is RAID 5. That's 4 plus 1. One more parity bit. We're XORing all these things to have one more parity bit. That's it. That's it. RAID 4 and RAID 5. So this is what we are trying to explain. RAID 4, we're just calculating a parity. A1 XOR A2 XOR A3 gives AP. Again, B1 XOR B2 XOR B3 gives BP, and so on. And RAID 5, in this we have diagonal stripe. So this is the basic difference between RAID 4 and RAID 5 with same number of disks. Now dynamic disk RAID 6. So what is this doing? This have two parity bits, and both of those parity bits are rotating inside. So dynamic disk pool, this was used in Wichita. So this was produced in Wichita NetApp. So this product NTAP E series was originally produced in Wichita in the NetApp. So RAID 6, 8 plus 2 under the hood. So it works as 8 plus 2 under the hood, but it's RAID 6. So this is the RAID 6 that was built here. So you can see here, both of these are rotating parties. See, this is all about. So as we discussed earlier in the earlier lectures, so the data that can be stored in 4 drives can be, given in more drives, can be given into more drives. For example, here, see, these are left alone. So 24 drive pool. So this was already discussed in the earlier lectures. So you should be aware of what this is. This 24 drive pool, they are allocating it randomly, and they will have a spreadsheet, a document explaining what drive each thing is explaining about and everything. Dynamic disk pools, NetApp Vista product, NTAPE series, which we just discussed, is the same slide. RAID 6, 8 plus 2 under the hood. P parity, Q parity is the diagonal parities. RAID 6 stripe 0 to DDP segments 0 to 7. This is 8th P, 9th Q. Stripe 1, data in DDP 0 to 6 plus 9. So this is how we are calculating in each of these parities, P, Q, in 8th segment. So metadata holds the information on where the data are. That's what we're discussing. They have a document that's called metadata. They'll just store the information where each of these data is located in the RAID. So this is the example. So orange DDP segment 0 to 9. So they'll store this information. Orange 0 to 9. Where is the orange located? So in one first block is the orange segment. So they'll have the data inside their metadata file. So this is the thing they are explaining. Metadata holds the information on where the data is stored. If one of the drive is failed, we are seeing these examples, we are trying to reconstruct. So they'll take the metadata, they'll exert the things based on the metadata, and they'll reconstruct it. Orange, red, green, yellow, brown. Okay. NetApp WAFL, WAFL, not really at RAID level. So we have more of the systems which are not RAID. So we can call it unconventional RAIDs. These are not actually RAIDs, but are used to store the data. One of that is WAFL. So if you are getting a job in NetApp, so they will be explaining WAFL to you if you are in the right department. So get a job that is right department to NetApp, you will get better knowledge. Write everything file layout. That's the full form of that. So write everything, everywhere file layout. So one more thing to discuss, why are we spreading the data in multiple drives if we can just stack the data in 4 or 5 different drives? So we are wasting these things here. Instead, we can just club it to form a 4 or 5 drives of RAID. So why are we like elaborating it into these many drives? Any idea on that? One is security. The data is more secured, so we just can't lose data. And one more thing, if we have more drives, there will be fast read and write operations on the disk. We can write and read fastly, so it's useful. So these are mostly used in SSD, but now HDD. Now everything is SSD, so it's not that useful now. But yeah, so write anywhere file layout since 1992. So it's the WAFL is a thing since 1992. Large cache memory knows about different file systems, APIs, ext3, FAT32, NTFS, HDFS plus, etc. So the old Windows system, the new Windows system, Mac OS, everything. So it knows about all the file systems. So it can be integrated with any operating systems. So examines incoming data, parses in nodes, etc. Knows which block constitute a file. So maintains internal metadata to show where the file is. So it maintains the internal metadata. So it has the documentation injected into the RAID, so everyone can see that and get to know which data drives are getting used. Now, there are many more non-standard RAIDs, not just WAFL. We have many more non-conventional RAIDs. So it's not like having formulas for every rate to store the data. We have unconventional rates as well. Some of them are really useful, and some are just marketing hypes. They're just releasing the products to market it. We're releasing a new product, but that's using the technology of 40s or 50s. So some of them are marketing hypes, and some of them are really useful. And the bottom line is we have more than two parities in a RAID, and we have saw that how to calculate. We'll just XOR the things for one of the parity bit, and for the other we'll just double the things and just triple the things later. So that's how they calculate the RAID triple parities. So they have more than three parities as well. So the documentations will be provided. There are papers published on those RAIDs, so we can just go through that and learn the mathematical concepts inside those RAIDs. So this lecture tried to explain you everything about the triple parity. So it's just to understand we have multiple parities, and we need to understand we have more systems that are unconventional to the RAID. So not everything is in the RAID. So yeah, so there are some which are very useful, and there are some which are just the marketing hypes. So that's everything about this lecture. So I said it's a short lecture. Any questions? People online or people in class, any questions on this lecture? I'm just going to stop recording now and start again.